Hello and welcome back. We are going to look at a couple of problems on flow processes using the first law for a controlled volume. So let's go on to the first problem here. So it says steam enters an adiabatic turbine at a rate of 10 kg per second at a pressure of 3.5 megapascal. The temperature is 350 degrees centigrade. At a point where the steam is at 1 megapascal, 250 degrees centigrade, 15% of the total mass is extracted and it is used to preheat water entering a boiler. The remaining of the steam is expanded further and exhausted from the turbine at 30 kilopascal with a quality of 90%. We are asked to determine the power output of the turbine. Okay. So let's see what this looks like. So we have steam which is entering an adiabatic turbine. So okay, let's draw a turbine. So a turbine, we said, is a device which has a shaft. There is expansion of some gas in the turbine which is generating work. So this turbine is adiabatic. So we indicate it as insulated. So steam enters here at a point, let's call it as 1. The rate is given. So m dot 1 is given as 10 kg per second. The pressure is given as 3.5 megapascal and the temperature is given as 350 degrees centigrade. So this is at 3.5 megapascal here and the pressure is reducing as it goes from left to right. So it says as a point where the steam is at 1 megapascal, 250 degrees centigrade, 15% of the total mass is extracted. So at some point here, this is some point 2. So m dot at 2 is 15% of the total mass which is coming in. So it's 15% of m dot of 1. The pressure at 2 is 1 megapascal. Temperature at 2 is 250 degrees centigrade. So this is given. It says the remainder of the steam is expanded further and exhausted from the turbine. So the remaining of the steam, so 0.15 m dot goes here, the remaining 0.85 m dot is expanded till some 0.3 where the pressure is, so we have m dot as 3 as 0.85 times m dot at 1. We have pressure at 3, it says it's 30 kilopascals. And it says quality at 3 is 90%, which is 0.9. We are asked to find out what is W dot. So we have now all of this information here. We are going to write down the first law for a control volume. We are going to look at this as a control volume. Our control volume is essentially this. There is mass entering at 1 point. There is mass leaving at 2 points. Okay, so let's write the first law. So that's the first law. We are told that this is an adiabatic turbine, therefore this can be ignored. So we will assume that this turbine operates in the steady state. So therefore this is 0. So we are left with this other expression over here. Minus W dot is equal to this, or W dot I can take to the other side. I am interested in finding out this W dot. So I have sigma mi dot. I have only one inlet. So I can get rid of the sigma and mi dot is essentially m1 dot. So this is h1 plus v1 square by 2 plus gz1 minus this other terms. There is no information given to me about the height of the inlet and the outlet. So I do not know how far from the ground Z1 is and Z2 and Z3. Usually as we discussed earlier, for turbines these are not significant. Changes in potential energy are usually small. So, I am going to ignore these changes in potential energy. So, this GZ1, the summation of these, I am going to take it as 0. I have also no information about the kinetic energies. What I am going to do is, I am going to assume here that the changes in kinetic energy are negligible, because for want of further information, what I am assuming is changes in potential energy and kinetic energy are negligible. So, then I do not have to take into account these. So, what I am left with is that W dot is M1 dot into enthalpy minus I have here M2 dot into enthalpy at 2 minus M3 dot into enthalpy at 3. So, this is essentially my first law. From the mass conservation, I have dm by dt is sigma of mi dot minus sigma of me dot. I am assuming this is a steady state process. So, this is also 0. Mi dot is essentially m1. So, I can take all of this to the other side. So, I get m1 dot is equal to m2 dot plus m3 dot. I know m1 sorry, I know m1 dot, it is 10 kg per second. I know m2 dot is 15% of the total. So, that is 0.15 into 10 kg per second, which essentially gives me m3 dot is 0.85 into 10 kg per second. So, this is how we got this here initially. So, I have this as 1.5 kg per second m2 dot, and this is 8.5 kg per second. So, now I can write this here. So, this is 10 kg per second into enthalpy minus m2 dot is 0.5 into 10, which is 1.5 H2, and this is this term here. So, 8.5 H3. So, I need to know the enthalpies at these points. So, I need to see what is the working substance I am using. So, the working substance here is steam. So, if the substance was air, I would use ideal gas law and Cp and Cv's to find enthalpy. Since it is steam, I need to find out these values from the steam tables. So, let us look at the steam tables. So, from the steam tables, I need the enthalpy at 1. So, the condition at 1 is a pressure of 3.5 megapascal and a temperature of 350 degrees centigrade. So, the temperature table 350 degrees centigrade. So, at 350 degrees centigrade, my saturation pressure is 16 megapascal. So, what we see is if the steam was at 350 degrees centigrade and a pressure of 16 megapascal, it would be saturated. My actual pressure is 3.5 megapascal, which is much lower than this saturation pressure. So, I have steam at this temperature. If I compressed it and kept it at 16 megapascal, it will be in the two-phase dome. It can come between liquid and vapor, but I am letting it expand so much. So, which means it is expanded much more than what it would be at that condition, which means that it is in the superheated state. So, what I need now is to look at this condition 350 degrees and 3.5 megapascal. I need to look at the superheated tables. So, in the superheated tables, let me go to 3.5 megapascal. So, this is 2 megapascal, this is 3.5 megapascal. I am interested in condition at 350 degrees centigrade, which is essentially this column, this row. I want enthalpy, it is 3104.8. This is in kilojoule per kg, this is in kg per second. So, kilojoule per kg into kg per second will give me something in kilowatt. Then I need, so this I found from superheated tables, I got this value. The next is H2. So, at point 2, the condition is 1 megapascal and 250 degrees centigrade. So, I am going back to the steam tables. So, 250 degrees centigrade and 1 megapascal. So, I see that at 250 degrees centigrade, if the pressure was close to 4 megapascal, it would be at saturation. Now, the pressure is lower than that, so it must be superheated. I can also see the same thing if I go to the pressure table and look at 1 megapascal. At 1 megapascal, if it was 180 degrees approximately, it would be saturated. I am at a higher temperature than that, so I must be in the superheated state. So, what I need to now do is to look at the superheated tables again. I need the table for 1 megapascal. This is that table. At 1 megapascal, I need 250 degrees centigrade. So, this is my entry. I want enthalpy. So, that is 2943.1 kilojoule per kg into kg per second will again give me kilowatts, and I have H3. So, at H3 it is already given to me that I have a quality, which means it is in the two phase region. So, what I want is enthalpy, which I can find out as something of this form. So, I need HF, I have X is 0.9 and I need HFG. So, I need this at 30 kilopascal of pressure. So, this is 30 into 10 to the power 3 pascals, which is 30 into 10 to the power 3 into 10 to the power minus 6 megapascal. So, this goes here. So, I have minus 3, so which is essentially 0.03 megapascal. So, I need these values at 0.03 megapascal from the saturation table. So, let me look at the things listed by pressure. At 0.03 megapascal, what I need are HF, which is 289.3, and HFG, which is 2335.2. Let me calculate this. This comes out to be, okay, so this term is 2391, which I put over here. So, now I can calculate out W naught. So, this comes out to be 6310 kilowatt. So, I see W dot is essentially 6.3 megawatt of power, which is being generated by this turbine under these conditions. So, let us go on to a different problem. It says here that a steam turbine is used to drive an air compressor as well as a generator, as shown in the figure. Heat losses from the turbine and the compressor as well as kinetic and potential energy changes can be neglected. Determine the power available to drive the generator. So, we have a steam turbine. We are giving it steam at high pressure and high temperature conditions and expanding it to low pressure and low temperature conditions. In doing this, this turbine generates work. Some of the work is used to run an air compressor, some of it is taken out to run a generator, which can then produce electricity. We are asked to find out what is this amount of work which is generated. So, again we can write the first law. We can take this air compressor and steam turbine both together as a control volume, or we can take individually as a control volume. It does not matter, we can take either of them. So, the dE by dt for the control volume is heat transferred minus work done plus whatever is coming in into the enthalpy and kinetic energy and potential energy minus whatever is going out into similar terms. I will assume that this device operates under steady state, which is usually the case with most of these kind of things. So, this is 0. What is said is that we can neglect heat losses from the turbine and the compressor. So, therefore, this is 0. It says we can also neglect kinetic and potential energy changes. Therefore, all of these together become 0. So, what I am left with is that W dot is This goes to the other side. So, I am left with this kind of an expression. So, the two substances are separate. So, this is air, this is steam. Okay. So, what I have is so I have an expression of this form. So, the steam and the air do not mix, steam comes in and goes out at some flow rate, air comes in and goes out at some flow rate. I have already used the conservation of mass. So, I have dm by dt separately for steam and I have dm by dt also separately for air in a similar fashion. So, which gives me this. So, I have m dot of air which is 10 kg per second into enthalpy of the air at the inlet minus enthalpy of air at the outlet. The enthalpy of air, I can take it as CPT because I am going to assume air is an ideal gas and I am going to assume that Cp is constant. So, enthalpy of air would be Cp times the temperature. So, the inlet it is Cp times 295, at the exit it is Cp times 550. And for the steam, the m dot is 25 kg per second. I have enthalpy at the inlet is 10 megapascal and 500 degrees centigrade, outlet is saturated at 10 kilopascal and 92%. So, I need to find out what is the value of again enthalpy of steam at this condition. So, 10 megapascal and 500 degrees centigrade. So, if I look at 10 megapascal here, the saturation temperature is 300, 500 is greater than that. So, it must be superheated. So, I want the superheated table at 10 megapascal which is here and 500 degrees centigrade. So, the enthalpy is 3375.1 from here. So, I have 3375.1 kilojoule per kg at the inlet. At the exit I can see what. So, the exit I have 92% as x, I have pressure as 10 kilopascal which is 10 in 10 power minus 3 megapascal which is 0.01 megapascal. So, at 0.01 megapascal I would have an expression of this form. I have something plus 0.93 into HFG. So, I need HF and HFG values at 0.01 megapascal. So, let me go to the pressure table. At 0.01 megapascal I want enthalpy values 191.8 and 2392.1. So, the exit enthalpy of steam I am going to calculate here. So, this comes out to be 2416.5. I need the value of Cp of air. So, Cp of air is gamma into R by gamma minus 1. I need the value of R. We have calculated this earlier as approximately 288. So, if I take R as 288 joule per kg Kelvin, so I get 288 into 1.4 divided by 0.4, which gives me a value of about 1008 joule per kg Kelvin. In most of these kind of problems, what we see is if you take a better composition, you will get a value of about 1005 or so, but I am going to use this value anyway. So, 10 into 1008, this is joules per kg Kelvin. These are in kilojoules per kg Kelvin. So, let me convert this also in kilojoule per kg Kelvin into 295 minus 550. So, this is about minus 2570 plus 23,966 which gives me a value of 21,395 kilowatt or 21.4 megawatt. So, what we see is that this turbine produces about 23 megawatt of power. Out of that, about 2 megawatt is gone into running this compressor, and the remaining is still available for running this generator. So, we have another problem here which says steam enters the condenser of a steam power plant at 20 kilopascal and 95% quality. Mass flow rate is about 20,000 kg per hour. It is to be cooled by water from a nearby river by circulating the water through the tubes of a condenser. To prevent thermal pollution, the river water is not allowed to experience a temperature rise above 10 degrees centigrade. If the steam is to leave the condenser as a saturated liquid as 20 kilopascal, determine the mass flow rate of the cooling water required, assuming the specific heat of river water to be 4.17 kilojoule per kg Kelvin. Okay. So, we have over here some kind of a heat exchanger. So, steam is entering here at 20 kilopascal with a quality of 0.95. The mass flow rate is 20,000 kg per hour. It is cooled by water from a nearby river. So, the steam comes here and goes out here. What it says is that the steam is to leave the condenser as a saturated liquid at 20 kilopascal. So, here it is coming in as with a quality of 0.95, here it is leaving a saturated liquid. What we are doing is, in order to cool this, so for example, you can think of this as coming into a tube like this and going out. In order to cool this, we are sending in river water from here, and the river water goes out. It cools these tubes and then goes out. The change in temperature of the river water so T3 is river water inlet, T4 is the river water exit temperature. It says that the river water is not allowed to experience a temperature rise above 10 degrees. So, what it says is that T4 will be higher than T3 because this river water is being heated by this steam which is condensing. T4 minus T3 should be less than or equal to 10 degrees. So, let us say it is equal to 10 degrees centigrade. What we want to know is how much of what is the flow rate of river water, that is essentially m dot 3, which is equal to m dot 4. We are considering this as steady state. So, any water which comes in from 3 must be going out at 4. So, m dot 3 is m dot 4. So, we have this, and that is what we want to find out. So, let us write the first law again for the control volume which contains all of this. So, we have the first law. This is a steady process, therefore, this is 0. We do not expect any heat transfer outside this device through the walls of this device for an ideal heat exchanger, therefore, this is 0. There is no shaft work, this does not expand or contract and do any work, there is no electrical magnetic work and so on, therefore, this is 0. We will assume that any changes in potential energy and kinetic energy are small, because we do not have any information about the areas of the pipes or the velocities of the pipes. So, these and these all put together, we are assuming that they are 0, which essentially tells us that sigma mi dot hi equal to sigma me dot into he. So, the inlets for us are 1 and 3. So, m dot 1 into enthalpy at that place, m dot 2 plus enthalpy at the exit should be equal to, sorry, m dot 3 is also inlet, exits are 2 and 4. So, m dot 2 times enthalpy at 2 plus m dot 4 times enthalpy at 4. So, this is essentially what we get as the first law. We have also mass conservation. Which is this, which essentially, and this has to be 0 at steady state. So, this essentially tells us that m dot 1 plus m dot 3, 1 and 3 are inlets, should be equal to m dot 2 plus m dot 4. That is also something which we have. In addition to that, what we have over here is that we do not have mixing of these liquids, because this would go back separately and this will go out separately. So, if we do not have mixing of them, in addition to this criterion, we have that m dot 3 should be equal to m dot 4 and m dot 1 should be equal to m dot 2. So, we also have that. Because they are different liquids. So, we need to also have this. So, at 1 we can find out the enthalpy. This is steam, this is entire thing is at 20 kilopascal. At 2 we know it is saturated liquid, so it is essentially HF itself. So, let us find out these values. The pressure is 20 kilopascal, which is 0.02 megapascal. So, let us go here to this table. Okay, we have 0.02 megapascal. The enthalpy of the liquid is 251.4 and 2357.5. This x is 0.95. So, we see that enthalpy of the steam at the inlet is essentially 2357.5. This is 2491 kilojoule per kg. So, we have here, we can also write these in terms of these other variables. So, we have m dot 3 is m dot 4. So, let me write this as m dot 3, and we have m dot 1 is m dot 2. What we are looking for is m dot 3. So, this is what we have. So, we have m dot 1 is 20,000 kg per hour. So, I am going to convert this into kg per second. So, there are 3,600 seconds in an hour. So, if it is this much kg in an hour, it would be this much by this much kg per second. H2 is saturated liquid at 20 kilopascal. So, this point would lie on the saturated liquid line on our TV diagram. If this is a 20 kilopascal isobar, this would be the liquid line, that would be this point. So, the value of that is 251.4 kilojoule per kg, and the value of H1 is 2491 kilojoule per kg, and denominator we have H3 minus H4. This is liquid river water, its temperature is very low. So, H3 minus H4 would be given as Cp into delta T. So, Cp of the water is given as 4.17 kilojoule per kg. Delta T we have said cannot be more than 10 degrees. So, this is 10. So, this is essentially the expression which we have. This is actually Cp T4 minus 3 is 10. So, this is actually minus 10. So, this minus and this term is negative, this term is negative, the negative signs get cancelled. So, we get an m dot 3 of about 298.3 kg per second, which if we multiply by 3,600, we get a value of about 1 million meter cube per hour. So, we see that we need a huge quantity of water to cool this steam such that the temperature of the water does not increase too much. This is of course something which we have seen all power plants, because we are trying to generate a lot of power to power the entire city. So, we need to reject a lot of heat, and if we make this water go out at a higher temperature, it will affect the surroundings, the surrounding water life and plants and fish and so on in a big way. So, we need to have a large flow of water, so that the temperature of the water does not increase too much in this process. So, this is a problem on heat exchangers using the first law.